Okay. Uh, this is physics, term 2, week 5. Uh, CA, you have 4.3.1 to 4.5.2. Then you have these grids, which make sure you do them because they are definitely going to come in the exam. And obviously the course division. I'm going to do quiz and notes. Okay. We're going to start 4.3. You start as transformers. Okay. Transformers. Transformers, you need to know they're basically devices used to modify an alternating current. You need to have alternating. If it's not alternating, the transformer won't work. Okay. So, for example, in other countries, the voltage is for like chargers is 110, but I think here in the UAE it's 220. So you sometimes like you need to use like European chargers. You guys know European chargers, they have only two, like they look like this and like this. It's the charger over here. You know the socket that you plug in, and it's like you plug it into the wall. You know it. But in the UAE and I think the rest of the Gulf, it's actually three. It's one here, and then this one at the top. It's like this, and you plug it in. Right. So this is because they take different voltages, and for that reason sometimes you need to put you can need to use a transformer in these devices. So that's just an easy way to remember what the transformer is. In other words, it transforms it, right? Changes. So alternating magnetic field, whatever, in a coil carrying an alternating current, the coil will behave as a magnet where poles swap every half a pair. That means it's alternating magnetic field, whatever. In basically in a coil, in an alternating current, since it alternates currents, since it changes direction, the magnetic field will also change direction, because you know that the magnetic field opposes the direction of the alternating current. So if the alternating current is going down, the magnetic field push it up, right? But you know, alternating current changes direction, so it's going down. Then alternating current goes like, you know what? No, I want to go up. Okay, so then the magnetic field will have to change its direction because it's always opposing it. Okay, that's basically what it says. The design of a transformer. Okay, transformer is very simple. You have a coil here. Okay, you have I'm just gonna read it. Okay, you have two coils wrapped around a soft iron core used for shunting the magnetic field into a secondary coil, and it is laminated to reduce eddy currents resulting in heating up and the transformer wasting energy. So I drew it over here. You have your primary coil and your secondary coil. This is your first coil over here. This is your secondary coil. Obviously, energy comes in, goes through the coil into the box, the iron core, and then it goes out. Ideally, the primary coil and the secondary coil have the different number of loops, because you know that the number of loops in a coil determines the induced current, right? You can induce the induced current by changing the rate of change of the magnetic flux. And to change the rate of change of the magnetic flux, it was in the periodic, use a coil with more loops. So the induced magnetic field induces a secondary EMF of the same frequency. Okay, the frequency is the same. Anyway, then there's these definitions in the book which you must memorize. They're also in the sample questions, which I will be sending later on for past exams. Memorize this all. I'm not gonna read it out. You can memorize this. How does a transformer work? Basically, an alternating potential difference is applied to the primary coil. The resulting current produces a large alternating magnetic flux, which links the secondary coil and induces an EMF in it. The value of this EMF depends on the number of turns in the secondary coil. Like I told you, let me go back up to my drawing. You're gonna have an alternating current go in. It turns, producing a large rate of change of magnetic flux. This change of magnetic flux basically sends the current over here to the secondary coil, where it goes out, right? Now, let's say مثلا here you have 20 loops. It's very simple. So here you have 20 loops, and then here you have 30 loops. So obviously here, since there's 30 loops, it's going to increase the EMF, and that's it. Since it has more loops, it's going to increase the EMF. But let's say here you had 20, but here you had only 10. That means it would decrease the EMF. So it all depends on the amount of loops, and you're going to see now. Over here, using the law of voltages. This is a nice formula you can memorize, okay? V out over V in is equal to NS over NP. Other people write it like this: V in over V out is equal to NP over NS. It's the same thing if you flip it. But my point is, it's easier like this to memorize. V out over V in is equal to NS over NP. NS is the number of turns in the secondary coil, and P is the number of turns in the primary coil. Okay, very, very simple. So let's say V out, let's say they told me V in is 20, 20 volts. They said that the secondary coil has 50 turns, and then they said the primary coil actually had 30 turns. Okay, and then they tell me, okay, find how much the V out is, right? So you're gonna go V out over the initial voltage 20 equal to the secondary one, which is 50 over the initial one, which is 30. Okay, it's easy to memorize for me because I say if up it's out, out is the second, like it's on the right, yeah, it's on the secondary. So obviously up here should also be secondary. So up here secondary, that means also here secondary. Okay. NS represents the transformer. What? NS represents the transformation coil. NP. Sorry. NS over NP represents the transformation ratio of the transformer. I meant to put it in a box. Okay, NS over NP represents the transformation ratio of the transformer. Sometimes that's why they call it, they just tell you the transformation ratio of the transformer is 4. You could see in a question like this. Okay, so then you just say, you replace all of NS over NP by like 4. You have two types of transformers. You have step up and step down. Obviously, for step-up transformers, you increase the voltage. That means the secondary, the number of turns in the secondary coil is greater than the number of turns in the primary coil. Thus, obviously, the voltage going out is greater than the voltage going in. And the transformation ratio is obviously greater than 1 because the secondary coil has more the loops than the primary coil. This is an example over here. This is your primary, this is your secondary. You see how the secondary coil has more loops than the primary coil. Step-down transformers obviously used to decrease. Here, obviously, the secondary coil will have less loops, and the transformation ratio will be less than 1. It's going to be a decimal. And obviously, the voltage going out will be less than the voltage going in because it's stepped down. Okay? And as you can see here, the primary coil has more loops than the secondary. Okay. Power in a transformer. Okay? Obviously, every electrical device has efficiency. Why does it have efficiency? Because nothing works 100% efficient. Nothing. So since a transformer is also an electrical device, it's gonna lose some of the voltage, some of the energy, okay, as heat or whatever. So we have this formula. Obviously, the energy going in is equal to the energy that's going out plus the energy lost. But they don't really ask this, but it makes sense. We have something called an ideal transformer, and we work on the basis that we're working with an ideal transformer. For an ideal transformer, the energy in is equal to the energy out. It's ideal. Ideal means it's the best. Okay, there's 100% efficiency. That means all of the energy that was put in was transformed and used and collected out. In other words, if energy going in is equal to the energy going out, that means the power going in is equal to the power going out. Okay? And you can derive from that a formula, because power in is equal to, P is equal to IV, right? So IV in is equal to IV out. And you can derive the formula. Now, this is I in, V in, obviously, and this is I out, V out. If you divide by V in on both sides, you're gonna get I in, V in with V in cancels, equals I V out over V in. And you guys know from our previous formula, V out over V in is equal to NS over NP, right? So we can replace this with NS over NP. Type. So I in is equal to I out times NS over NP. Okay, let's divide by I out on both sides. You can get I in is over I out is equal to NS over NP. This is how the formula is derived. Okay, you're not responsible for this. You can just memorize the formula and go to the exam. Just know, for voltage, they're the same. So secondary. But for current, it's the opposite. So when it's secondary up, it's you're using the current going in. Okay. So this only applies for ideal transformers, because when is this true? It's only true when power in is equal to power out, and that's only when you have an ideal transformer. What are the characteristics of an ideal transformer? It's 100% efficient. Its power going in is equal to the power going out, and it has this formula: I in over I out is equal to NS over NP. It's always NS over NP, but no, for voltage, it's out over in, but for current, it's in over out. And obviously for no energy is lost. Okay, now transformer efficiency. These are just questions. This question لفت لي نظري. I don't know if they ask it in the quiz, but these are just characteristics of a transformer. Okay, you need to know these four. I'm gonna go. You need to know the transformers only work with AC. They don't work with DC. They ask why is it laminated, the iron core. You know how it's wrapped with an iron core to reduce eddy currents. Okay, and obviously good magnetic linkage. And then they ask for the formula, very easy. And they ask for what's the frequency going out. Remember, the frequency never changes. It's 50 hertz as well. Okay, obviously you don't see the question here, but no, I just wanted to show you. Transformer efficiency. I don't remember them asking a question where you actually use the formula, but you know that the efficiency is equal to how much power out over power in, right? Let's say, and I put in 100 volt, 100 watt, and out I only got 80 watts. But what's the efficiency? Obviously 80 over 100 times 100%, right? Which is just 80%, which makes sense. I'm sure you don't even need a formula to know efficiency. It's very easy. An ideal transformer has 100% efficiency. We know this. This is just applications to find the turns, whatever application of formula. Okay, now electrical generator. You know, a generator converts mechanical energy to electric. Okay, you start spinning and you get electric. In power stations, generators use the principle of electromagnetism. Okay, this is all يعني هبل. Most generators use 3 sets of armatures. This is in the book. I'm just going over it. I don't know if there's questions on it, but I'm going to go over it for the sake of going over it, okay? So most generators use 3 sets of armatures. So this is 1, 2, 3. The angle between 2 armatures is 120 degrees. I don't know, these are just notes our teacher gave us. Each coil has 2 terminals, 1 neutral, and the 3 others... Okay, so I'm reading over this, and I'm reading out, like, it doesn't really make sense, but just memorize this. It never came from what I saw. You can memorize if you want, but just know if it comes. Electrical generators use the principle of electromagnetism, okay, because that's the blue text in the book. Note that the angle between each armature is 120 degrees, okay, and just know each coil has 2 terminals, one called the neutral, which is 0 volts. The others give 3 different outputs called live phases, okay, just know this. And an electric generator, I don't see this in the book. But no, it's just know this. An electric generator is either a stationary big coil or strong violating electromagnet, which is a rotor. Okay, whatever. Okay. هلا this is the annoying part. I think it's wiring. Transmission. Okay. Power transmission. Okay, power is lost when power is transmitted through power lines, where power lost is equal to Ri squared. Obviously. I'm pretty sure you've seen these photos before. You're transmitting power through these grids, okay, and you're always gonna have power lost, because power lost, you're transmitting a current through a wire that has resistance. So power lost equals Ri squared. For a reducing current by a factor of 10, the power lost will be reduced by 100. You see, because power loss is equal to Ri squared. So if we reduce the current by 10 times, the power loss will reduce by how much? By 10 squared, right? So that's why to transport a car, okay, that's why we can't blast wires with too much current, because it's gonna lose power, right? To transport a constant power, voltage must increase by using a transformer. This is done to decrease the current. So if you increase the voltage, you're gonna get the same power, because when you increase the voltage, the current is gonna go down. So when the current goes down, power lost will also decrease, But since I'm increasing the voltage, there's gonna be more power. So that way I won't be losing power. In other words, to transport the constant power, just note, to transport the constant power, since we can't play with the current, we're gonna increase the voltage, which will allow the current to go down to reduce the power lost. Okay, that's it. To transport the constant power, voltage must increase. You need to change the voltage by using a transformer. Whatever. These are just okay questions solved in the book. Okay, for the national grid, and I said see page 37 because I'm not gonna draw a lot. It's over here. Before I go to national grid, I was looking at the book, and I'm gonna explain to you. Basically, they didn't really explain the last section. The last thing I explained was about increasing voltage. They said to understand, solve this activity. Okay, so question one, basically they're saying a town requires 10 megawatts of power. Okay, which is 10 times 10 to the power of 6, because mega is 10 to the power of 6. So in other words, it's 10 to the power of 7 watts. Okay, they said that the VRMS is 10 squared volts, so 100 volts, right? Use P equals VI to find the current flowing. How do we find current? I is, if take V to the other side, I is equal to P over V, so 10 to the power of 7 over 100, or 10 to the power of 2, which is 10 to the power of 5 amperes, right? Okay, now they said, okay, you have the current, use P equal Ri squared to find the power wasted. R is equal to 1, okay? P is gonna, power loss, right? So P is equal to R1 times 10 to the power of 5 squared, because Ri squared. So it's gonna be, power loss is gonna be how much? 10 to the power of 10 watts. Then, now they said the VRMS is 10 to the power of 5. Again, repeat what you just did, but use 10 to the power of 5 instead. Find the current. Again, we use the current. I is equal to P over V. So 10 to the power of 7 is the power. It's the same power, but now we just increase the voltage. So divided by the voltage, 10 to the power of 5 is equal to 10 to the power of 2 ampere. Now determine the power wasted. Same formula. Power lost is equal to Ri squared, so the resistance 1, times I squared, so 10 to the power of 2 squared. So you're going to get 10 to the power of 4 watts. So see how when the voltage was 10 squared, the power loss is 10 to the power of 10. But when the voltage is 10 to the power of 5, the power loss is only 10 to the power of 4. So basically, the more you increase the voltage, the closer you are to conserving the power and increasing efficiency. Okay? For the national grid, okay. The national grid, I drew up until here. Okay, I'm gonna read over it with you, and it's a lot, so I'm just gonna summarize and highlight and whatever. Okay, so I read over it, and I'm just gonna go zoom into this because it summarizes all this text. So on Earth, in almost every modern country that has electricity, even Lebanon, you have this, what we call the national grid. I'm pretty sure you've seen it, especially if you're in the UAE, if you're maybe taking a road trip, or maybe even going to Dubai from Sharjah. I go from Sharjah to Dubai. I see many of these big towers and whatever. So how it starts is everything starts over here where they produce the power in the power station. Let me make this bigger. In the power station. Okay. Oh, that's ugly. Okay. In the power station, right? In the power station, it starts at 25 kilovolts. Okay, that's the potential difference. But when it leaves the power station to be sent, it's obviously not going to leave at 25 kilovolts because خلاص, by the time you reach the house, you would have lost it all. Well, you're going to need more than 25 kilovolts in other places. So 25 kilovolts, when it leaves, it goes through the transformer. This actually shows the importance of the transformers. It steps it up to how much? 400 kilovolts, right? When it's 400 kilovolts, this is the highest it's ever going to attain. And this is where we call the super grid. So the super grid sends to all of the country, okay? And it has 400 kilovolts. Then it goes down to a normal grid where it's met by a step down transformer, steps it down to 132 kilovolts. Okay, so now خلاص, we're going to start sending it for actual electrical use. The first place it passes by is obviously the heavy industry because we're going to slow down slowly. So let's start with the biggest, heaviest things that we need to use, and it's the heavy industry that uses around 33 kilovolts, where again step down transformers are used to decrease it to 33 kilovolts. Then after that comes the light industry, where it's met by 11 kilovolts and it's met by a step down transformer. Then you go to towns to power up buildings and villages and whatever, and farms, where they all use the voltage we use in our houses, and that is 240 volts. So I hope you understood that. Very simple. You need to know two things. These cables are called pylons, okay? And they are insulating material that don't allow leakage. That's the first thing. Well, let me erase it. I'll actually show you where they said this in the book so that you guys don't be confused. Over here. So to prevent current leaking to the ground, they hang on pylons. Okay, as shown in the diagram, these are pylons. You need to know that this is sets of three. Okay, they're carried in sets of three because it's a three-phase alternating supply. Okay, at the top, the cable at the top is called what? The neutral wire, and its whole presence is just to complete the circuit. Okay, is to complete the circuit and link all the tops of the pylons together. Very simple, national grid. Okay, now here, advantages of three-phase transmission lines. Okay, why do we use three-phase? Why do we use these three cables over here? Let's see. The three cables have a neutral wire to close the circuit at the top, right? This is very important. You need to know this. What are the three advantages? Alternators are made such that they give even more output power. They need only one neutral wire to complete the circuit, and since the neutral wire is thin, it reduces costs and power loss. So, alternators are made such that they give even more power. So, when you have three wires, you get more power because you have alternators. There's less power lost. Also, why is there less power lost? Because when you use three-phase transmission line, the neutral wire you use is thin, which makes it less expensive and it reduces the power loss. The thicker a wire is, the more power going to be lost. And if you're using 3 instead of 5 and 10 and whatever, you're only going to need one neutral wire to complete the circuit. Someone's going to come and say, I'm sure, someone's going to come and say, why don't you just use one wire for the whole thing? Kid, you can't rely on one wire. You can't. You really can't. Okay, then why the wires cannot be made thinner? If you make a wire thinner to reduce the resistance, you make the wire thinner, right? When the wire becomes too thin, it won't be able to transmit current, so it will melt. So you need to find a compromise between too thin and too thick. Let's see, I think this is the last thing I need to do. Over here. Okay, so you have house wiring and you have circuit breakers and fuses. Okay, so earth wire, we don't do it. Okay, house wiring, this is very boring, so there's a lot of memorizing in it. These are 7 things you need to know by heart. The first thing in house wiring, is the incoming cable. The incoming cable, as we know, it's 3 lines cable that supplies electricity to your house, right? You have the live, neutral, and earth. Okay, 3 wires. What are they called? Live, neutral, and earth. I'll show you the book for this because I don't want to rely on my notes and miss something over here. Okay, over here. So the first thing is the incoming cable. Okay, it has 3 wires: the live, neutral, and earth. In most of the countries, the potential difference is 240. Okay, except USA, because they're always trying to be different, these Americans. The potential difference between the live and the neutral and the frequency is 50 hertz. That's the normal standard one. Sometimes the cable includes 5 lines, 3 phases, neutral and earth, in which case we have a 3-phase electricity with potential difference. Okay, that's boring. Let me just check something. Yeah, so over here in the notes, I wrote, for when they have 5 lines, that's actually when you have some light in the street. Okay, they have 5 lines. When I say 3 phases, that means 3 live wires. Okay, 3 live, and then 1 neutral and 1 earth. You always have 1 neutral, 1 earth. These are always something you have. Okay, but standard for heavy industry, we don't want to split it up, so we just use 3. Then you have the main fuse. The main fuse is a protective device fixed to the live wire. It may be 50 amperes or more, and it's usually sealed by the board. Only a qualified The main fuse protects both electricity meter and okay. So this makes sense. Yani. It's the main fuse. You can't touch this. You're not allowed because you can get electrocuted easily and whatever. Then you have the electricity meter. This records how much energy consumed in kilowatt hours. It's somewhere in your house, and it shows, maybe not in your house but connected to your house. And when your parents pay the electricity bill, the company actually reads the electricity meter and charges you based on how much kilowatt hours you have consumed. The circuit breaker board, I'm sure many of you have seen this before in your house. I have one. I'm seeing it right now. It's right beside my room. And this is basically where you can turn on and off parts of the house. So basically, I'm gonna use this one as an example. This is a nice example. See how it says A1, A3, A4, A6, B4, whatever, whatever. Basically, on most modern circuit breakers in my house, beside my circuit breaker, I have like a paper, and it says A1, kitchen, A2, bedroom 1, and bedroom 1 is like my parents' bedroom, and then B4 is toilet, and then B5 would be water heater, and so on and so forth, right? So this is actually how it goes. So this is the label. So let's say مثلا I have a wire in the kitchen that's faulty and it's causing everything to turn off. So I go to A1 and I just switch it off. That way it won't interfere anymore with everything else. It won't take electricity. Uh, Sometimes there might be even a circuit breaker for an individual device, like I showed you, water heater, or in my country in Lebanon, we have a circuit breaker just for the air conditioning, because it takes too much electricity, so we turn it on and off. Appliances have one or more independent circuits coming from the fuse box. For example, the electric cooker and water heater may have independent circuits, one for each. This is like what I said now. My water heater, it would have its own circuit breaker. Okay? If storage electrical house heating and off-peak water heating appliances are used, the heating units may be fitted with separate electricity. Okay. Appliances. That's what appliances are. Cooker and water heater. You should know they have separate circuits.
Show me your other hacks. Show me your
Radial circuits for lighting. Radial, like radiation. So that's why I remember it as lighting. Because lighting requires small currents. So it has its own circuit called the radial circuit. Since your light needs very, very little current, it has its own separate circuits. Ring circuits are for sockets which usually consume a higher current. Okay? Ring circuits, when you put your charger in the wall, that's what a ring circuit is. Very easy. So, ring circuit versus radial circuits. I think I have this in my notes. It's very they talked a lot in the book, but I'm gonna just use my notes. A ring circuit is used as a power circuit, feeding many other sockets. Its advantage is to feed all outlets from both directions, which reduces the load on the cable. That's pretty much it. A ring circuit is big and it feeds these small radial circuits. Let me show you. So a ring circuit is a power feeding many outlet sockets. In a ring circuit, there's three wire. You have. Oh my god. Okay, so without talking too much, I'm just gonna summarize this, and I need the pictures. That's why I opened the book. Basically, the difference between ring and radial is you can see this small part here. Okay, this part is open in radial, but in ring it forms a ring shape. It continues. Basically, how it works is you have the circuit breaker over here. You start over here. It goes down and it feeds both directions simultaneously. That's why it's one of the advantages. It feeds both directions. But here it has to go down and then come back up. It can't just skip this. Okay, so it reduces the load by feeding all directions. And what's the other one? It feeds many outlet sockets. They both feed many outlet sockets. This one goes one by one by one by one. This one can do many at once. Okay, I think you guys can recognize what these sockets look like. This is the thing you put into the wall. We call it a socket in real life. Come on. Okay, now circuit breakers and fuses. Okay, fuses are in series, they must be placed on the live wire, and their purpose is to resist and protect eddy currents. This is how a fuse looks. Okay, I need to show you the book because really you won't understand without the book. Okay, fuses, they must be placed on the live wire because that's where the current is, right? Switches must always be placed on the live wire as well. When the circuit is open, it becomes isolated from the source of electrical energy. You need a switch. If you don't place the switch on the wire, then how's the switch gonna open and close the circuit? Okay. I said circuit breakers, open page 43, okay. Over here. Okay, so in summary, for circuit breakers, this is what a circuit breaker looks like, and there's one in the circuit breaker board that we spoke about earlier. A circuit breaker, it has it's very important, extremely important. There are two types. There's something called an overload circuit breaker, and there is the electric leakage, earth leakage circuit breaker. Very, very easy from the word. I'm gonna start with overload. Overload circuit breakers, basically there's springs. In the circuit breaker, there's a spring. When there's too much current, when the current flowing rises more than expected, the circuit breaker, the spring, actually is like look. You have, this is the circuit breaker. Inside of it, there's a small spring. Okay, this spring, it's taut, or like it's kind of compressed, or like, yeah, it's compressed. Okay, when it's compressed, that means there's current flowing. But sometimes when there's too much current flowing, it's an electromagnet. Don't forget, it's an electromagnet. When there's too much current flowing, there's going to be an increased force, right? Remember, IBF. So there's going to be increased force. For that reason, the spring is going to pop. Okay, think of it like that. When the spring's going to pop, it's pulled aside. The others, like, there's two springs. There's this one and another one. It pops, and basically this switch goes down. Okay, and that turns off the whole circuit. So basically, this is useful when مثلا there's an error in the circuit, and for some reason there's too much current being produced. It pops the circuit and turns it off, which makes you aware that, oh, there's something wrong. The other type is called the ELCB. Okay, earth leakage circuit breaker. If you put water, if now you threw water into your socket, or a computer charger or whatever, you're gonna realize electricity turns off. Why does it turn off? It turns off because of the earth leakage circuit breaker. It detected a change in electric conduction. Okay, how it works? The ELCB has a spring. This spring, it stays where it is as long as the currents in the live and neutral wires are equal. But when you throw a drop of water into the earth, into the socket, whoa, it changed. So that means the spring is triggered, and it pops, and the ELCB, it switches off. If you try turning the LCB back on, it's gonna turn on for a millisecond and realize that, oh, still there's a problem, and turns back off. Then that's when you go and check, maybe there's water in the current, and you call your electrician, and he comes and checks your devices. هيك بنكون خلصنا هون. I'm gonna go and do the quiz, and we're gonna go through this a bit quicker. Okay, here we have drag and drop, whatever, induces an EMF, helps in linking the magnetic field of the primary with the secondary, helps in generating an alternating magnetic field. Okay, obviously the one that generates alternating magnetic field is the primary coil. The one that has an induced EMF is the secondary coil, right? Remember, the primary coil generates the alternating magnetic field and sends it to the right, which the secondary coil gets an induced EMF. And obviously the soft iron core, we said, is the one that links it. These are all wrapped around the soft iron core. Question 2. A transformer has 760 turns in the primary and 100 in the secondary. Based on the number of coils, it is a what? If it's more in the primary and less in the secondary, that means it's obviously step down, right? There's two types, step up, step down. Okay, in order to decrease losses of energy in power transmission from the power plant through the grid, certain measures must be taken. So the amount of loss of energy in the wire is proportional to what? What's this power loss equal to? Ri square. So the square of the current and the resistance, right? In order to decrease these losses, what do we use? Step-up transformers are used. Why do we use step-up transformers? Remember, we're trying to increase the voltage, right? You want to increase the voltage in power transmission. To increase the voltage, what do you use? You use a step-up transformer. Okay, step-up transformers are used, and as a result, you're going to have higher voltage and lower current. Question 4. Use the transformer equation. Okay, a transformer has 60 turns in the primary coil and n turns in the secondary coil. The peak EMF in the primary and secondary coils are 48 and 240. So here you had 48, here you had 240. Okay, they want us to find the number of turns in the secondary coil. Remember, the formula is V out over V in is equal to NS over NP. Let's go. V out is 240, V in is what? 48, NS is... we don't know how much is NS, and P is 60. If you cross multiply, you should get 300. Yeah, you get 300. You get 300 turns. The current in the primary coil is 4 amperes and the current in the secondary coil is 0.72 ampere. What is the input power of the transformer? Obviously, the input power P is equal to IV, right? The current is 4, the voltage is 48, so 4 times 48 is 192, right? What's the output power of the transformer? The current is 0.72 and the voltage is 240, so 0.72 times 240, same equation, 173. They asked what is the efficiency. How do you find efficiency? 173. You always, efficiency, P out over Pn times 100%. So 173 over Pn 192 times 100%, right? And you get 90. Very easy questions. Question 5. Okay, new device and whatever. Okay. Protects people from accidental electrocution based on the principle of electromagnet. Obviously, electrocution, it's the circuit breaker. But which one? Earth leakage. Okay? Earth leakage. The other one was overload. But overload, the other name is called electromechanical. Okay, the overload, remember I told you the one about overload. The name of it is called electromechanical circuit breaker. In other words, electromechanical, electricity, mechanical means movement. Okay, so electromechanical overload. So, electrocution is earth leakage, right? The one from overload is what? Electromechanical circuit breaker. Okay, protects from overcurrent by melting down is the fuse. So yeah, it's the fuse over here. The fuse, yani we said the fuse, it must be always placed on the live wire. What the fuse did, I didn't explain it. Basically, the fuse, it's like the circuit breaker. Until when you place it on a wire, it's very thin. If there's too much of a large current, overload, the fuse melts and the circuit turns off. Okay, that's just how it works. These are very, very, very easy. No, nothing too hard. Memorization, all easy. Question 6. 0.8 kilowatt washing machine works on 220 volts main supply. The current flowing through it is 3.6 ampere. Which of the following fuses is most suitable to use for protection? Of course, if you have 3.6 amperes, you're not going to use, this is the wrong answer, 3.6 amperes. Because if you use 3.6 ampere, what if you get a small eddy current and it goes up to 3.7 ampere? Then the wire is going to melt. So you should always leave room for error. So 3.6 amperes, put a 4 ampere fuse, right? We're using fuses, huh? What's the whole function of a fuse? A fuse melts if there's an increase of current. Okay? If there's an increase of current by 0.4, then okay, that's when there's a problem. But if you use a 3.6 fuse, the current might go up to 3.7, might go up to 3.8. You wouldn't want the fuse to melt just because you had a small 0.1 error. So if it goes up to 4 amperes, that's when you know there's a problem, right? So you can't use a 3.6 fuse for 3.6. Use a 4. Okay, the table below shows the current and voltage in the coils of a transformer. What is the efficiency of the transformer given to the nearest integer? Remember, efficiency is equal to P out over Pn times 100, right? Pn is equal to I in Vn, right? So see 2.2 times 9. The secondary coil is 162 milliampere, so 1.6, it's 162 times 10 to the power of negative 3, right? Because milli is times 10 to the power of negative 3 times the voltage 110. Use your calculator. 2.2 times 9, you get 19.8, and then here you have 0.162 times 110, 17.82. So this is P out and this is Pn. Use your formula, P out over Pn, so 17.82 times 19.8 divided by 19.8 times 100%, get 90. Okay, when you're doing times 100% in the calculator, don't actually put the percentage symbol. Okay, so 90%. Question 8. An ideal transformer is connected to 220 volts, 50 hertz supply. The primary windings have 100 turns and the secondary has 2000. What is the output voltage? Okay. If they asked what is the frequency, because I remember seeing a question like this in a past exam, they asked what is the frequency. I think it's here. Wait, let me open it. Yeah, over here. So, oh my God. So over here, an ideal transformer is connected to 220 volts, 60 hertz. So in the exam, they asked what is the frequency, and what you should know about the frequency of the transformer, it is never changed. Okay, so if they ask for frequency, it stays the same. Type here they're asking for the voltage, so obviously we're going to use the rule, the formula. V out over V in is equal to NS over N. So V out is, we don't know, over V in 220 is equal to NS over NP. So if you cross multiply, you should get times 20. Yeah, you're gonna get 4,400. Question 9. If a secondary coil has more turns than the primary coil, then what is the transformer called? Obviously, step up transformer, right? Question 10. When the transformation ratio is less than 1, the transformer is called what? Step down transformer, right? When it's less than 1. Question 11. So what's transformation ratio again, guys? It's NS over NP. So when NS over NP is less than 1, that means you're stepping down. Question 11. A network of power lines that are carried overhead on pylons are what are they called? Carry electricity for all over country. Obviously, it's called the national grid. You can see any of these. Question 12. To prevent current leaking to the ground, right? What do they use? They hang on long insulators. What are they called? Pylons. These pylons are insulators that prevent leakage. The input voltage of an ideal transformer is 12 volts. The number of turns in the primary coil is 100. The number of turns in the secondary is 650. What's the output? Again and again and again. Formula V out over V in. V in is 12 is equal to NS over NP. NS is 650 over N primary. Again, this is the formula, in case for some reason you don't know it. Okay, cross multiply and you should get 78 volts. Type شو undefined? I don't know. Based on the number of turns on the transformer, what type of transformer is this? If the number of turns in the secondary coil is greater than that of the primary, then obviously it's going to be a step-up transformer, right? Question 14, I think, and 18 questions. Yes. A step-up transformer, obviously, what does it do to the voltage? Does it increase or decrease? It increases the voltage. An ideal transformer, what does it do to the power? It doesn't change, because remember, an ideal transformer, P in is equal to P out, right? A real transformer, you know that in a real transformer, P in is equal to P out plus P lost, right? So that means obviously P in will be greater than P out, right? So it's decreasing the power. Why is it decreasing it? Because it's some of it is lost. Is it decreasing by a good amount? No, just some of it is lost due to friction and heat and whatever. If a transformer increases its output voltage, what does it do to the current? Obviously, it decreases the current. Power, same thing, same way as power. If you're increasing the voltage, that means it's going to be a decreasing current, right? Memorize. Question 15. So we have voltage and we have the highest and to the lowest. Obviously, the highest is the supergrid, and then it goes to the grid, where the grid supplies to the heavy industry, and then power station output. Power station output is the least, right? But compared to others, let's go back to our photo. It's over here. Power station output is 25. The lowest is where it's power station output, and the lower than that is the light industry, and then lower than the light industry is the farms and buildings and villages that we use. Okay. Question 16. Yeah, so here towns are 11. The light industry is 11. What? Here towns is 11? Yeah, this 11 is for towns as well. Okay, so towns is for light industry towns, and then 240 is for farms and villages. So villages, towns, and light industry, you can just say they're 11. Okay, so towns and light industry are 11, 11. When you think towns, think of buildings and whatever. New York, Dubai, and whatever. Heavy industry is obviously 33, and then super grid is 400. An electrical device that changes the voltage is what? Obviously transformer. These questions are so easy. Which of the following correctly describes the danger it presents? What's this? This switch shown is deemed unsafe to be used in the shower room. حلف? Which of the following describes the danger? Why can't it be used in the shower room? Because the electricity can flow through the switch due to water splashes. You can get electrocuted. You know, water is a conductor, right? So when you splash water in the shower, it may conduct electricity and electrocute you. How can this situation be fixed? Install a pull switch with a long cord of insulating material. Okay, which I've seen before. I've definitely seen this before. Shower rooms, the light there, they use what do you call it? They use the pull switch. Install the switch outside the shower room, obviously that being the most obvious. That's why I'm not sure about you guys, but in most houses I've been to in the UAE, the lights, like the switch to turn on the lights for the bathroom or toilet, is actually outside the toilet. It's not inside. Put a fuse on the neutral wire. Why? شو خص neutral wire? Add the neutral wire. Again, شو خص? The neutral wire is just there, to support, to prevent, to reduce power loss. Use a sensor switch that requires no hand contact. I guess that's, yeah, that makes sense. So this way, if you're not placing your hand on it, that means there won't be any water on it, unless you deliberately get a bucket of water and splash it. Question 18. Consider an electric circuit diagram of domestic appliance. Both ammeters show a current of 2.5 ampere when the switch is closed. Where should a fuse be installed to protect the whole circuit? Remember, fuses should always be placed on the live wire, not in parallel, please. Not in parallel. Okay? If it's in parallel, that means if the switch turns off, if the fuse turns off the circuit, it won't turn off the whole circuit. The whole reason of us using a switch is to turn off the whole circuit, so it must be placed in series, always on the live wire. Choose the correct answer. The most appropriate fuse to be used in the circuit is marked how many amperes? Obviously 5 amperes. You have 2.5 ampere. So in total, it should be 5 ampere. A 20 ampere fuse was installed by mistake in its correct place. What happens when the circuit is switched on? The fuse will always not blow, but the circuit will be unprotected. If you put a 20 ampere fuse, the circuit will continue as it is. عادي. But what the problem is if you have overcurrent, to 8-9 amperes, it will be unprotected and the circuit will have melting, whatever. So for that reason, it will remain unprotected because خلاص you use the 20 ampere fuse. Sure. What's the point? How are you a jump? No way the circuit is gonna overcurrent all the way to 20. You know what I mean? Assuming the appliance is indeed safe to use, underline the symbol that is printed on it. It should be this one. This wasn't in the book from what I saw, but it was in a previous exam question. I don't know, maybe they put it somewhere here. I can't see it anyway. I really can't. Okay. Oh yeah, here. So it's in 4.5.6, and it's the symbol for double insulation. Okay, know this because I saw it in a previous exam, but actually it's not required for our material because we only have till 4.5.2. Okay, week 5. Whoa. Okay. Where am I? Here. So when something is safe to use, this is the symbol and it means it's double insulated. That's it for this one, this quiz. Please make sure you go over these good questions. If you're not gonna go over all the course questions, just go over these good questions at least, okay? And خلاص, that's it. Thank you so much for watching and good luck.